almost the youngest you can be. So how old are you? 22. It's 85. Is it? Well, that excludes me. People just use millennials. Oh my god. There's just some of those millennials.
I wonder if I can change the resolution.
You're gonna try and make it stream 4K.
No, I wanted to get faster, so I might cut this down. Oh,
Oh my god.
man.
Yeah, that is 4K.
That's some precise pen drawing there.
Go down to the bottom one.
6-1.
Oh god.
See how that looks.
So let's see, 1980.
Mm-hmm.
It's on a motion
GED
stand.
help video.
We can make Clippy. That's,
GED help. Yeah, like OPD. This is the direction you need to go.
You're gonna cut down the delay too?
yeah, hopefully. And the file size. I've been uploading like 4 gig files.
I didn't even know what GED was. Why are these adults doing simple math?
All right, let's see how that works. Nice.
Yeah, now you're just like, back then they okay, old man.
All right, so let's do node deletion. Wow, what happened to my windowing? That works. Let's talk about deleting nodes from a binary tree.
Why are you let's get something that don't worry about it.
This isn't important, I just like doing this. All right, there's a big binary search tree, wow. Okay. So 20 is the root of the tree here, and we want to delete a node. Okay, if we're deleting a leaf node, it's easy. Right? We want to delete the 11, just get rid of the 11. Just change this thing to point to null. Okay, so there's some nodes that are very easy to delete. If we want to delete the 10, it's a little harder. If we want to delete the 20, it's really kind of daunting looking because we lose the root, right? What are we going to do? And we can't really just put the 40 up here because the 10 would have to go to the left of the 40, and it's already got something on the left. So in the abstract, this can look like a fairly cumbersome process. But in reality, there's a really simple algorithm we can use to delete a node. So to delete node n, where n is the data value. So we basically remove it. So first of all, we only look at the tree rooted at that node. Okay, nothing else is going to change. So look at Subtree rooted at n. So let's say we want to delete the 10. We're going to remove the root. So we're just working on this tree right here. We're going to remove the root, and we're going to replace it. And we have two ways that we can do this. We can replace with the largest node on the left, or with the smallest node on the right. So if we use the smallest node on the largest node on the left, that's just a 5. It's going to move the 5 up into the root, and this is still going to be a fine binary search tree. We'll have 5, and then 12, 11, and 14. And everything there is less than 20, and we haven't changed anything on the right side. So that will be pretty easy. If we were to use the largest node on the right, that would take the 14 and put it up here. And we still have a fine binary. We don't have a fine binary search tree. Smallest thing on the right. So we put the 11 up here, and now we still have a fine tree. 5 is smaller, 12 and 14 are bigger, and we haven't changed anything anywhere else. All right, suppose we delete the 40. So we're looking at this tree over here. And let's just stick with the largest node on the left. Okay, what's the largest node on the left of this subtree? 14 is not part of it. 40 is the root. What's the largest node in the left subtree? 35. So we're going to get rid of this. We're going to replace it with 35. But there's a problem here. If we delete 35, 33 has been orphaned, right? We moved its parent. And 35 can't bring its child 33 along with it because it's got a new child 30, right? And it's also got a child on the right, but it's got a child on the left. So 33 has been orphaned. But that's not too bad. We can have it be adopted by 35's parent. And that's always going to be an option. Because we picked the largest node on the left, that means whichever node we pick cannot have a right child. Because if it had a right child, that node would be bigger, because bigger things are to the right. So the node that we choose to move to the root will not have a right child. It will only have, at most, a left child, which means that we can take the node that was pointing to 35 and basically replace the 35 with the 33, its left child. And it's a very general algorithm. If there's no left child, the left child still exists, it's just null. And when we replace 30's right child to be null, it's just like removing the 35. So the algorithm is completely general. So find the node you want to delete, consider that subtree, find the largest node in the left subtree, replace the root with that, and if that node itself had anything to the left, put that to the right of that node's parent. And so here's what this can look like in a more extreme case. So there's a quirky looking tree. And let's delete the 29. Or let's delete the 40. So we're going to find the largest node in the left subtree, which is going to be this 29 right here. So we're going to put 29 up at the root, and then we're going to have this orphaned entire family that used to be the left child of 29. But since we know that 29 had nothing to the right, we can take 20 and we can have it adopt all of 29's children on the right. And now we've got a binary search tree again. So delete n. Now let me write this out. So delete n. So we move to the subtree rooted at n. So we're always deleting the root of a tree. Okay, it's a subtree. Find largest node x in left subtree. Replace n with x and replace replace basically x with x's left child. So find the largest node on the left, move that to the root, and in its place, put its left child. So over here, to delete the 40, we find the largest node is 29, move that up to the root, and then replace the 29 with all the stuff that was on its left, which was the 28 rooted tree. And that's always going to work. And it's going to work because the largest node is not going to have anything to the right. Right? If it did, if there was something hanging off here, then we might not be able to move 28 up here because 28 might already have something to the right. But since we know 29 is the largest, it's only got stuff to the left. So if we move all that up in place of 29, we don't lose anything. And it's the identical process if we take the smallest element in the right subtree. And we know that when we do that, that smallest node cannot have a child to the left. Because if it did, it would be smaller than the node. And when we do this, we're adjusting pointers. We're not copying data values. We're not copying the number 29 into this node's data. If we do that, we've still got a node here, and we could copy this node's data value into this node's to make that a 28. But we'd still need to come down and copy a 25 into here, and a 23 into here, and then put a node here for a 26, right? That's a mess. We're really moving the nodes around themselves, right? So we pick up this node, and we put it there, and we have it adopt whatever was to the left of the root as its left child, whatever was to the right as its right child, and then we move the 28 up to where that 29 was. Yeah?
So after moving the 29 up to the top,
Mm-hmm.
we assume 29 is x, and we say x now equals x's left, which would be 28. Would that mean that x's left also then changes to 25 after that? Because
You might probably need some extra variables in there. Right, so I'm being a little sloppy in here. Find the largest node x in the left subtree, replace the root with x, replace where x was with what the old x's left child was. But if you're actually writing code to do this, you can't change x and still use it down here. Does that make sense? Okay. There's a lot of housekeeping to keep track of in here. We can't just replace 29 with this new subtree, right? We need to know where 29's parent was. It was this node, and then we need to set this node's right child to be this new subtree. So as we're marching through finding this biggest node, we need to know where we came from at each point, just like when we put something into a linked list. We know that this is where we want our node to go, but we need something more than that. We need to know how we are pointing to this. So we've got to sort of remember one node back. And then there's this business of finding the largest node in the left subtree. And that can be a tricky business. But basically, go ahead. Yes. Yes, and that's going to be very useful. So you can have two-way pointers so that each node points to its children, but each of the children also back points to its parent. More housekeeping when you do operations, but it's very convenient. And when we start balancing trees, maybe next week, maybe in a few weeks, we'll probably be thinking about trees that have both pointers, because we're going to do so much going back and forth in the tree, because we'll need to find siblings and uncles and aunts and things like that. So those will make it handy. Thanks. So how do we find the largest node in a tree? Right, we're going down to the left subtree, but in general, we've got a tree, and we want to find the largest node in that tree. So do I still have my really crazy looking tree? There's my really crazy one. Here's the whole tree. How do we find the largest value in here? Just keep going right. Go to the right, go to the right, go to the right. Can't go anymore. That's the largest value. Smallest node, go to the left, go to the left. Can't go left anymore. That's the smallest one.
So 57 can't have a right child that's 62.
It can't because 57 is sitting to the left of 60. Everything to the left has to be bigger than, has to be less than 60. So that may make quick sense, and then you may doubt it later. I doubt it every time I say it, but I think it works. So just go to the right as far as you can. So this business of finding the largest node in the left subtree, in this case would say go to the left subtree and then just start moving to the right as far as you can. That's how we got to 29. And it could be that there's nothing to the right, in which case the root is the largest value in that subtree. Right? If you have a tree where everything is to the left of the root's the largest value. So you may end up going right no times. And these are all edge cases when you write code for this. Okay, tree node deletion is definitely a case where you have a lot of edges to deal with. So, and that'll be part of PA4. So, but you'll be fluent with dealing with pointers and nodes and drawing pictures. So then you can concentrate on grappling with the algorithm itself. And it feels really good when you get it to work. And you had lots of seg faults before then. All right, so deletion we will talk about more when we start writing some code for this stuff, which we'll do probably next week.
Well, didn't we already write the code for insert, search?
Yeah, we wrote recursive code for those, yeah, so we need to do delete still. But I don't want to do it today. It's too nice out. All right, so questions on that? So let's look at some applications of trees. One application of trees. And we've already kind of alluded to some of this. So whatever that is, A plus B times the quantity C plus the quantity D times the quantity E minus F. That's an algebraic expression, right? This is the form that we learned to write in school. So this is algebraic notation. And we can represent this with a tree as follows. We can make a pair of children whose parent is an operator. So this tree represents the expression E minus F. We have two operands, and then we have a parent, which is an operator. And it says apply that operator to those two operands. So this is E minus F. And if we want to multiply that by D, we can have a D, and we can have the result of this, and we can say multiply. And this tree corresponds to D times this tree, which is E minus F. So that's this part of the expression. And if we want to add a C to that result, we can have C plus all of that stuff. And we can make a totally separate tree, which is A, B, and a plus. And that's this expression right here. And if we want to multiply those two expressions together, we can simply make them children of a star. Can't believe that worked out. So this tree corresponds to this algebraic expression. And it's really saying our expression is the product of two things. One is the sum of A and B. The other is the sum of C and all of this, which is the product of D and this, which is E minus F. So that's algebraic notation. And if we were to traverse this tree in order, we get something like A plus B star C plus D star E minus F with no parentheses. And that's a different expression because we have an order of operations. But here's the cool thing. If we were to traverse this in post order, left-right node, let's see what we get. We're going to start at the root. We're going to come all the way to the left, and we'll get an A. And then we'll go all the way to the right and get a B. And then we'll visit the node. And that's the traversal of the left subtree. Now we're going to traverse the right subtree. And traversing this tree, we'll start off by going to the left. And then traverse the right subtree, which will start off by going to the left. And then traversing the right subtree, which will start by going to the left. And then the right, and then visiting the node. And we've done the left and right subtrees of this, so we visit the node. And now we've done the left and right subtrees of this, so we visit the node. And now we've done the left and right subtrees of this, and so we visit the node. And that is the postfix version of that algebraic expression. So if we have our stack-based calculator, we can evaluate this expression from this traversal of the tree. So you take A and B and you add them, you take C and D and E and F, you take E and F and subtract them, you multiply by D, you add C, and then you multiply by A plus B. So this is one way we can take algebraic expressions, convert them into this reverse Polish notation, postfix, and then we run that through a stack-based calculator, and we can actually evaluate the expression. So that's a handy use for trees and different traversal orders. All right, so building a tree. So our insert routine, I already put away my insert code. Our insert code, we say insert 10 into an empty tree. And our code would say if the root is null, which it is, make a new node, set it equal to 10, return that. So our first node is going to be, say, a 10. And if we insert a 10 and then a 5 and then a 20, the 5 will go here, the 20 will go here. And then if we insert a 3, it'll go left, left, right here. And 15 will go right, left, and here. And a 7 will go left, right, and here. And a 25 will go right, right, and here. And this is the tree we end up with. But if we happen to insert in this order, our tree looks very different, right? We start off with a 3, the 5 goes to the right, the 7 goes to the right twice, the 10, the 15, the 20, and the 25. So we saw this before. As a binary search tree, it represents the same set of information in the same order. But this tree looks fundamentally different from the tree above. And the big difference is performance. If we search for something in this tree on top, let's say we search for the number 18, is it here? No. It'd be to the right, it would be to the left of this, or it would be to the right of this. It's not found. It takes 1, 2, 3 operations. If we search for an 18 in here, it would be to the right of this, 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 and it's not found there. It takes 5 operations. And if we happen to search for the number 30, here we're going to have to compare to 1, 2, 3, 4, 5, 6, 7 things before we find that it's not in there. Whereas here, it's not a 10, it's not a 20, it's not a 25, it's not in our tree. It's still only 3 operations. So this tree on top looks somehow more balanced. It's equally full on both sides, whereas the tree on the bottom looks really lopsided. You'd call your landscaper and say, hey, something's wrong with my tree. All right, why is the one on the bottom worse performance? It's basically an array or a linked list. Every time that we search for something, we start at the root, we say, should we go to the left or the right? Well, we're cutting our data in half, usually, but what we're really doing is we're descending one level in the tree. So up here, we're starting at the root. This is a depth of 0. Whether our number is less than 10 or bigger than 10, we're going to come down here or here. We're going to go to a place where the depth of these nodes is 1. And when we make another decision, we'll descend to a spot where the depth is equal to 2. The height of the tree is the maximum depth. So if the height of this tree is 2, we know that we're going to have to do a total of 3 operations before we're at a leaf. Right? Well, 2 operations compared to 10 and 20, and now we're at a leaf. And we do one more operation. And if we're at a leaf, there's no children. It's either the number we're looking for or our number is not found. So worst case when we search a nicely balanced tree, worst case when we search any tree, the number of operations we need is the height of the tree. Okay, so worst case. Search takes H comparisons, where H equals the height of the tree. So trees with less height are going to be faster to search. Now both of these trees have 7 pieces of data in them, but the one on top has a height of 2, the one on the bottom has a height of 6. So what we're really interested in is storing a bunch of information in a tree, but trying to keep the height really small as possible. So we can describe whether or not a tree is as short as possible. We can make that rigorous. And so this is something called a balanced tree. So what does it mean to say that a tree is balanced? Well, intuitively, it means that it's about as short as it possibly could be. If we were to rearrange the data, preserving the sort order, we always want to preserve the sort order. If we were to rearrange the data, could we get a tree that was fundamentally shorter, had a smaller height? If we can't, then the tree is going to be balanced. So here's a formula to tell if a tree T is balanced. So if we find the height of the left subtree and we find the height of the right subtree, and we look at their difference and we look at the absolute value of that, it's got to be less than or equal to 1. And we're not done. This is that Indiana Jones thing. There's another side to this. And the left subtree is balanced. And the right subtree is balanced. And those are both important, because otherwise right, the left and right subtrees both have the same height. So that satisfies this first condition. But this left subtree itself is definitely not balanced. And that's good, because in fact this whole tree is definitely not balanced. The height of the subtrees is the same, but we're not taking advantage of all these other points where we could have more data filled in. Right? We want to sort of fluff it up and spread it out. So we also require that the left and right subtrees are balanced. Or T is null. Because this is an endless rabbit hole, right? If we want to know if T is balanced and we say, well, is the left subtree balanced? Well, to answer that, we're going to have to look at the left subtree of the left subtree. And to answer that, we'll have to look at that thing's left subtree. And if we just do that endlessly, eventually we're going to blow up. So the other way in which a tree can be balanced is if the tree is null. So a tree containing no roots is balanced. That's our base case. That gets us out of the recursive descent. So that's a recursive definition for balance. Tree's balanced if the left and right subtrees have heights that are close to each other within 1, and the left and right subtrees are balanced, or the tree is null. Yes? Oh, that's a whole nother story. And we are going there. Mm-hmm.
You just grab the number in between, like the middle-sized number, and put that at the root. Do that over and over again.
Sort of, but doing that is tricky. But that's kind of what happens. But there's some subtleties in how we make that happen. But I think we'll have time to touch on it today. All right, well, let's play with this definition of balance a bit. Everyone agree that's going to be balanced? Well, let's start with this, right? Is that a balanced tree? Better be, right? There's no other way to represent a tree with one node than just a root. Well, the left subtree is empty. What's the height of an empty tree? -1, right? It's that weird quirky case. So the height of an empty tree height of null is -1. So the left subtree and the right subtree both have height -1. That satisfies that property that their heights are the same. And the left subtree is null. We said a null tree is balanced. Right subtree is null. We said a null tree is balanced. That satisfies all the properties. So this is balanced. All right, this tree over here, the left subtree has height 0. It's just a root. Right has height 0. That's fine. And both of these are balanced because we just confirmed that a root-only tree is balanced. So this is balanced. What about that?
I was not balanced.
So this tree has a height of 1, this has a height of 0. So the heights are close. 12 is balanced, but is this balanced? Yes, because this has height 0, this has height -1, so they're close. The left subtree is 5, that's balanced. The right subtree is null, that's balanced. So that's balanced. And since this is balanced and this is balanced and their heights differ by 1, this is balanced. And in fact, that's going to be balanced too. And it never feels like it should be, because it's starting to look like the two linked lists, right? But if you apply this definition, right, since this is balanced and their heights are both 1, left and right are balanced, heights are close, this whole thing is balanced. But now we start getting into edge cases. Well, if we do pretty much anything else on here, it's going to unbalance us if we do anything at the leaves. So if we throw, 12.5 down here, right? So this thing, the left subtree has height -1, the right subtree has height 2. Is that right? Left subtree is null. Yeah, right subtree has height 2. So that's not going to be balanced because the heights don't match close enough. Let's see.
You say it's because 12 left was null, which is -1, and then
Yeah, now I'm starting to wonder about that. This is definitely balanced. Oh yeah, left subtree. Okay, so the left subtree of this has height -1. The right subtree is this, which has height 1. Right, -1 and 1 differ by 2. That's too much of a difference. So that's not balanced itself. But if we were to do something like this, or let's put an 11 down here, right, that's still going to be balanced. So left and right subtrees both have height 1. This we already saw was balanced, and this we already saw was balanced. So that'll be balanced. So the feeling here is that if we can kind of keep filling in things at a higher level before we do too much on a lower level, things will look balanced. And I'll just give you a preview, and then we'll talk more about height.
real quick on the last tree,
Yeah.
the 12.5 one that wasn't balanced.
Mm-hmm.
If you had the tree above it and you were inserting 12.5, how would you be able to insert 12.5 with keeping it balanced?
That's what I'm about to do, but I changed my numbers so I don't have evil decimals. So here's our tree, and we want to insert a 17. And our normal insert algorithm would put it right here, and we'd end up unbalanced. Okay, here's what we're going to do. We're going to do what's called a rotation. And this is called a left rotation. And we're going to rotate about this point. The idea is, if we just look at this piece of our tree, we have 15, 20, 17. And that's unbalanced. But this tree is equivalent to this tree. It's got the same sort order, 15, 17, 20, 15. That doesn't work. Boom. 17 goes there. What do we rotate around? Oh, it's a left-right. Never mind. Anyway, it will turn it into this. Okay, so that's got the same sort order. And we'll basically replace this with this. So we'll end up with everything over here being the same. But instead of a 15, 20, 17, we'll have a 17, 15, 20. And that'll be nice and balanced. And an easier to see example of that would be inserting a 25. We'll throw off our balance. But this is easily replaced with this. And this is what we're going to call a left rotation, because the idea is we're taking this and rotating it down, and we're bringing this up to the root. So we're taking these chain of 3 things, and we're basically turning it into that. So 15, 20, 25, and we just kind of put 15 on the left, bring 20 up to the root, 25 stays on the right, and now this is balanced. And when we put that in its place, the resulting tree will still be balanced. But this one where we added something hanging off the left, that's going to take 2 rotations to correct. So here's the idea. If we start off with a balanced tree, whenever we insert or delete, there's a possibility the tree will become unbalanced. But in that event, we can always restore balance by 1 or 2 operations. We can do either a left rotate, a right rotate, a pair of lefts, a pair of rights, or a left right or a right left.
Do we need to check balance every time?
Yes. And once you've inserted more than one thing, it's possible your balance is so far off that you can't simply use a rotate or a pair of rotates to restore it. So we're going to need to keep the thing balanced every time that we make a change. And if we do that, it's going to be an order 1 operation. And that's going to make things nice. But there's going to be 4 types of operations we do: left, right, and right, left. And it's a few pages of going through examples and lots of different colored pens and things like that, and I don't want to do that now. I think we'll do it later on in this course. If not this course, we'll do it in 223. But just know that there is a way to do this. It's something you do every time you add or remove from the tree, and it basically does an operation like this to bring your balance back. So it would turn this into that.
Is it just like a couple if statements and changing pointers?
Yeah, and it's really easy to draw with pictures, and it's a little frightening to make in code because there's a lot of housekeeping. But the concept is pretty straightforward, and we basically break it down into a set of cases, and we describe the balance factor at each point. So at each point, we can look at the height of the left subtree minus the height of the right. And that should always be within plus or minus 1. As soon as it's bigger than 2 or bigger than or equal to 2 or less than or equal to -2, that's where we need to make a correction. And then based on what your tree looks like at that point, you do one of these 4 sets of operations.
To get the height, are you like having a counter and then you traverse it? Or?
Yeah, so let's talk about height. Etc. So we want to find the height of some tree T. It's a struct node star, whatever. I'm going abstract. We want to find the height of this tree. Well, if you look at any tree, it's always got a left subtree and a right subtree. They could be null, or they could be a big million node collection of things. If we have this subtree with a certain height and we add a root on top of it, what's the height of that new tree compared to the height of just this subtree? It goes up by 1. And if we have the height of this tree and we add a root, the height of this new subtree is the height of the old subtree plus 1. So the height of the entire tree can be found as follows. Find the height of the left subtree. Find the height of the right subtree. If the height of the left subtree is greater, then the height of the entire tree will be the height of that subtree plus 1. So return 1 plus the height of the left subtree. Else, return 1 plus the height of the right subtree. So in this case, the right subtree was bigger, so the height of the left doesn't matter. If we take the height of this right subtree and we add 1, we get the height of the entire tree. So there's an algorithm for finding the height of a tree. Basically, find the height of the largest, find the largest of the height of the left subtree and the height of the right subtree, add 1, return that. That's your height. And it's nicely recursive. And it will blow up royally if we don't add one more thing to this. Say again? Yeah. So what's the...
T null.
Yeah. So if we do this, right, first thing we're going to do is take the left subtree and find its height, which you're going to come in here, look at the left subtree of that, and call for its height. And look at the left subtree of that. And if we keep doing that, we're going to get to the leaf node. And if we do the left subtree of a leaf node, it's going to be null. And when we say t arrow left, it's going to segfault. So we got a base case in here if t equals null. Return the height of a null tree, which is conveniently minus 1. Why is that convenient? Because if we have a tree that looks like this, the left and right subtrees have height minus 1. Add 1, we get the height of this, which is 0. So the reason a null tree has height minus 1 is because that's 1 less than the height of a tree that has just a root. And it makes things like this work. So you can technically write all this in a single if-then-else statement if you use a ternary operator or a max function. Getting the idea that recursion is useful for this? Your alternative is to traverse the tree, and every time you go down to a child, add 1 to a counter, and keep track globally of the deepest depth that you've gone. And then when you're done with your traversal, whatever the deepest depth was, right, that gives you the height. And that's a lot of code. And it's all the overhead of traversal, plus it's keeping track of this global level, which you have to actually do with a stack or something, because you can't just subtract 1 when you come back out. And this is just, right, it's almost the definition of height. It's 1 plus the height of the deepest tree, or the tallest tree. So we got a recursive formula for height. We've got a recursive definition of balance. We've got recursive insert, search, traverse. And we can do a recursive delete. So we have to write the actual code for deleting the root. But assuming we've done that, what can we say? So delete root, comma num. And this is going to have to return a struct node star. Because remember, our root is pointing to the root, and if we happen to delete the root, then that's going to have to point to something else. So we're going to want to return the address of the new root. So if, well, we'll throw our edge case in here. If root equals null, return null. But if we make sure that the thing is in our tree before we delete, we should never get to a case where we're trying to delete from an empty tree. So that may be optional. So if our number is equal to the root's value, then do all the stuff we talked about. Find the largest node on the left, replace the root with that, and replace the node that you moved to the root with everything that was on its left. Or go on the right. Okay, and return root, whatever the new root is. Okay, so this is deleting the root. Otherwise, if our number is less than root data, well, let's delete from the left subtree. How do we delete our data from the left subtree? Call our delete function. And that's going to return the new root of the left subtree. So we're going to say root left equals delete, and then just return root. Otherwise, our number is bigger than the root, so delete from the root right subtree. And that'll return the root of the new right subtree, so set root's right subtree to that, and return the root. So the stuff we talked about, moving the largest node from the left to the root and so on, that's all this top part, right? That's when we actually want to delete the root of a tree. If we want to delete a node and it's not the root, just call delete. Pass it the subtree and say, hey, delete from this tree for me. And then put it back into the correct subtree of your root, and you're done. So it's a combination of some recursive calls, but then also all that stuff that we're going to have to do to actually delete the root of a tree. And at some point, as we keep calling this, delete from the left, delete from the right, we'll get down to that point where this is the node we want to delete, it's the root of a subtree. We'll make all those adjustments, and whatever we end up with, that takes the place of that subtree. And then we pop out of our recursion, our head comes above ground, and we're done. All right, so we'll have to add a lot of meat to these bones, particularly for deletion. But that's an overview of it. I don't know where exactly I want to go next week, because I know you're still working on PA3, and I don't want to get too gory with PA4 until you're actually in a place where you can be writing code. And so if you're still working through PA3, I want to let you do that. So we may switch gears next week and then come back to this the following week when we're ready to actually start PA4. But we'll see. If we switch gears, we'll probably talk about hashes, which is tied in with associative arrays. And that's good stuff to get through in between. All right, cool. I will see you next time. And I have office hours until 3, so if you want to come talk to me, feel free.